Hello and welcome to this video lecture series on microprocessor and microcontroller. And we are currently studying the 8086 microprocessor. And this is 18th video lecture in the complete series and 8th video lecture for 8086 microprocessor. In the previous video, we have studied the minimum mode of operation of 8086 microprocessor. And by minimum mode of operation, we mean that in the complete circuit, we will only have one microprocessor, which will be 8086. Rest all will be peripherals or externally interfaced memory. So that way, if we make our microcomputer system, that system will be called as in minimum mode of operation. Similarly, there is an other mode in which various other processors can also be coupled with this 8086 microprocessor, and that mode is called as maximum mode of 8086 microprocessor. So maximum mode, as we have also discussed earlier, is used to interface several other things like 8087 math coprocessor. Then there is a input output processor, etc., which we are going to see. So there are various things which can be coupled with this 8086 microprocessor to enhance the capability of the complete circuit that we have constructed, right? So before beginning, let me just show you some slides for the pin diagram, where we will first again distinguish between the maximum and minimum mode of operation in terms of the pins that will be used. So here you see the pin diagram of 8086 microprocessor, and to be able to operate this microprocessor in maximum or minimum mode, as we have already discussed, that the pin number 33 has to be set or reset accordingly, right? So if the value at this pin is 1, then it is operating in minimum mode of operation. That means a single processor mode of operation, or otherwise if it is 0, then it is operating in the maximum mode of operation or multi-processor mode of operation, right? And all of the pins will have same meaning for both of the modes, except for the pins that you see from uh, pin number 31 to pin number 24, I mean 24 to 31, right? So whatever is written inside these small brackets, it is applicable for your minimum mode of operation, and we have discussed this in the previous lecture together with the timing diagram. And the same thing we are going to do for this maximum mode of operation, where this request comma grant pin will be used, rq slash gt 0, and this request slash grant pin 1. So this is used by the external devices like external microprocessors or external peripheral to gain the control of this 8086 system and internal buses, etc. So in that case, the priority will be given to request grant 0. In case there are two occurrences of requests from various devices, then in that case, the priority will be first given to rq slash gt 0, and after that rq slash gt bar with 1 will be served, right? Then we have lock pin. We have understood the meaning of lock pin. When microprocessor 8086 is not willing to give the control of its internal buses to the external world, then the lock pin will be floated high, and this will be known to the external world through this is status pin. Then this S0, S1, and S2, these are the status pins which this microprocessor has, and according to this S0, S1, and S2 status, this microprocessor will be performing the input output read or memory read, input output write or memory write, or interrupt acknowledge cycle. So the status of this S0, S1, and S2 will let us know that. So let us first have a look at those relevant S0 bar, S1 bar, and S2 bar status pins. So here you see that for various combinations, we have these values: interrupt acknowledge, read input output port, write input output port, then halt, instruction fetch, read memory, write memory, and passing inactive. So we have already discussed this in one of our lectures, the meaning of these relevant status pins. So these status pins will be used here. Then this QS0 and QS1, we have already said that this QS0 and QS1 will be used with your status of your queue, I mean instruction queue that is there in microprocessor. So I think that those slides are also there. So let me just bring those relevant slide. Yeah. So this QS0 and QS1, it tells you the status of the 6-byte instruction queue that we have seen in the architecture of 8086. So for 00, there is no operation which is performed on queue in the last executed instruction. For 01, the first byte has been taken by the last instruction. For 10, the queue has to be emptied, and for 11, you have to access the subsequent byte, right? So this is what we mean by these pins, and they can be used in this maximum mode of operation. So we will see that in current lecture we will see the operation of maximum mode, and we will find it highly similar to minimum mode, with some differences in the hardware implementation, right? So these control signals, sorry, these status signals that you see here, S0, S1, and S2, they will be applied to one IC, and that IC will be generating the control signals for the external world. I mean, how this 8086 microprocessor will deal with the external world. So those are all the things that we are going to see in current lecture. And let me first again show you what we did on the last turn. So this was this minimum mode system which we studied on the last turn, and we saw that to be able to operate a microprocessor, we first need to have a clock, clock 8284 IC. So this 8284 IC is the clock generator IC, and we saw that the pins that we had an output from this IC are connected to the clock ready and reset, and these all of these were at different frequencies, right? So the work of 8284 IC here is to just simply, provide the appropriate frequency to the appropriate signals. And we had this PCLK output from here also, which was for peripheral clock. It is not shown here, but it can be used, right? Then after applying this clock, we had these latches, because we saw that in T1 state, in T1 timing diagram state, we have to latch the addresses. So for that, since the addresses in 8086 are of this 20, they are of 20 bits, so that is why we need to have these three such latches here, because individual latches will be having a capability of 8 bits or 1 byte. So we had these three latches, and so 20 bits out of those complete available 24 storing capacity will be used there. And then there was a transceiver. This was an optional device, but more or less it is used with this microprocessor, because it is used to strengthen the signal that we have received from here. And since multiple devices are interfaced with this microprocessor, so they can all draw their signal from this transceiver. Then we have odd and even memory bank of addresses which are of this storage, externally stored external memory are connected, and then input output devices were there together with their address selection logic. And regarding the timing diagram of this minimum mode, what we have studied was uh, this for the minimum mode of operation. As we can see here, let me just show you the relevant slides here first. So this is for the minimum mode of operation. So if you can see, for minimum mode of operation in T1 state, the main purpose is ALE has to be enabled, and that will enable the 8282 latches, and 8282 will latch the addresses. So in the first timing state, or first T state, the main purpose that happens is the address that has been floated on the address bus is latched onto the external 8282 latch. Then in T2 state, what the main purpose is that this DEN signal has to be enabled. DEN is lowered. DEN bar is lowered means DEN is enabled, so that the transceiver can be enabled. And the appropriate signals of read and write have to be activated. Whatever we want to perform, they have to be activated or deactivated. Hence, sorry, activated, not deactivated. Hence, this AD0 to AD15 go through high impedance state. So when you have activated these signals, then in that case, this AD0 to AD15 won't have any meaning, and they will go to high impedance state. In T3 state, the actual data transfer happens, and insertion of additional wait states in between T3 and T4 if it is required. If the device which is externally interfaced is slow, then in that case this is required. And in the T4 state, what happens is you clear the signals, basically whatever signals have been set for a particular operation. So DEN bar will be raised high, so that your transceiver IC will be deactivated. Then read write signal will be raised high, not read write bar signal will be raised high, so that they are deactivated. And for the next T1 state, you will be setting the memory or the input output signal so that you can do it accordingly. So in today's lecture, we will see that for maximum mode of operation, this all will be valid, but there are some changes in the hardware. So it will be, all of this thing will be achieved through a different set of hardware. So I will show you this chart for this maximum mode also as of now. So this is the chart for maximum mode. We will discuss it once we discuss the hardware part, but we will see that most of the things are similar here. ALE is enabled in first T state and addresses are latched. Then this DEN bar is set as 0, and then the data transfer actually happens in T3, and additional T states are introduced if it is required, if the peripheral device is slow, and then in T4 state you have to finally deactivate your signal. So essentially the same operations happen in that mode also, in maximum mode also, but they are achieved through different hardware. So the signals that you notice here, AMWC bar, AIOWC bar, etc., I will make the meaning of all of these clear, and then we will come to the slide again. Right. So let me just go on to this maximum mode operation of 8086. Right. So you see here, this is not the complete diagram that I wanted to show, but this is just a part. We will further elaborate this diagram. So to begin with, this is a good start. So let us see. So here you have got this 8086 CPU. So this is your 8086 CPU, and this is the diagram for maximum mode of operation. So obviously, if it is operating in maximum mode at the maximum or minimum pin, you need to ground that signal, because MX bar or the maximum mode will be on when you have ground here. In the earlier case, if you see, in the earlier case when we were using minimum mode, we have applied VCC here. VCC corresponds to positive logic. Logic value 1, and this ground correspond to logic value 0. So since we want to operate this in maximum mode, so the first thing that we will do is we have to apply a ground signal here, which is logic level 0 value. After that, we have to apply this clock, which is 8284 clock generator, and it will be applied in the exact same way as we have done for minimum mode of operation. So this clock is independent of maximum or minimum mode of operation, so I am not discussing it in detail further. The explanation remains the same. Now, looking at the two old ICs which are familiar to us, which are 8282 latch and 8286 transceiver, right? So these two are the old familiar ICs that have been come from minimum mode again, but now this time they are not directly controlled by the microprocessor. However, they are actually controlled by this 8288 bus controller, right? So this is a new device that has been introduced here, which is called as 8288 bus controller. So this 8288 bus controller, it actually takes the status signals S0, S1 and S2 from this microprocessor 8086, and it converts them into appropriate memory read, memory write operations, etc. here, right? Because in the table we have seen, in the table for statuses of S0 bar, S1 bar and S2 bar, what we have seen was the for different 8 values of these S0, S1 and S2, different operations were performed. So this 8288 Intel bus controller IC will actually do the same job for you. It will generate the appropriate signals, right? So let me just discuss the relevant outputs of this 8288 bus controller. So the inputs are these, and the outputs you can see here: MRDC. MRDC means M for memory, RD for read, and C for your command, memory read command. So this is memory read command, MRDC. Similarly, MWTC, this is called as memory write command, right? So all of these are active low signals. So memory read command, memory write command. Then you have advanced memory write command, and correspondingly you have advanced input output write command, right? So these two are similar signals: advanced memory write command and advanced input output write command. So why do we call them advanced? So the reason is, if you have a slow peripheral which is interfaced with this microprocessor, then that peripheral, if you want to write something onto that peripheral, we will be providing signals through these two pins, AMWC bar and AIOWC bar, which is advanced memory write command and advanced input output write command, so that it gets additional one clock cycle for getting prepared, right? So when you provide them when you provide them signals at these two pins, whether it is externally interfaced memory or input output signal, so if that is slow, then in that case, through these signals, if you provide the output to those inputs, to those devices, then it will get an additional t state to get prepared for that transfer. However, you can see that you have signals like IOWC, which is input output write command, and IOWC is input output write command, and there is an advanced version of this. So IOWC, you do not get any additional t state for getting prepared for transfer of data, because if you provide output through this particular pin, then in that case it is assumed that your input output device is fast enough to catch up with this, right? So that is the difference between advanced mode and normal mode. So IOWC is already there, and you can see that IORC, that is input output read bar, it is also there, right? And INTA bar stands for interrupt acknowledge, and we very well know what is the purpose of that. If any interrupt appears here, and if the interrupt flag is set inside microprocessor, and if it is a uh, non-maskable instruction, then it is accepted and it is acknowledged at this particular pin. If it is a maskable instruction or a non-maskable instruction, if interrupt flag is set, INTA bar it will be acknowledged. But if interrupt flag is 0, then for maskable interrupts, the interrupt will not be acknowledged and INTA bar pin will not be appropriately set. So this is the meaning of all of these pins. And if you notice here, there are certain outputs which are called as DEN, DT/Q, and ALE. So they all come from this particular 8288 bus controller. Because if you see again, the pin diagram of 8086 IC. So in this 8086 IC, there was, in the maximum mode, there was no ALE, DT/Q, and DEN, because those pins had different meaning there. So let me just show you that diagram again, so that whatever I say will make sense. So let me just put it in the slideshow mode. Yeah. So if you see this thing here, so this ALE, etc., DEN bar, etc., they were all valid for this minimum mode of operation. However, in this maximum mode of operation, there is no ALE, etc., ALE or DEN bar or pins of DT/R, etc. So, but ultimately these pins should be there, because ultimately then only the address latching will happen. So they are not there because in this mode of operation, this same functionality will be provided by this 8288 bus controller. So these are the output pins, DEN, DT/Q. Then you have to transmit the data or read the data, and this ALE pin is there. So these are the outputs of this 8288 bus controller, and these are connected to the 8282 latch or 8286 trans receiver, right? So this complete bus controller will be controlling the operation of this latch as well as this trans receiver. So this is one major point of difference between minimum and maximum mode of operation. So there are various pins in this, as you see. Now, one might ask a question that in maximum mode of operation there should be multiple processors, but you only see this 8086 processor here. So I will answer that shortly, because this is not the full configuration that you are seeing here. That full configuration I'm going to show you in a little in a while. So, but before that, let us now discuss the operation of this complete 8288 bus controller. Let me show you the internal diagram of this 8288 bus controller, and let us discuss what are the individual things that you see here, and what are their meanings. So this 8288 bus controller essentially that you see here, this is the 8288 bus controller, whatever is enclosed within these boxes, and these pins that you see, ALE, DEN, DT/R, then MCEP, DEN bar, etc. All of these pins are the outputs. S0, S1, S2 are the inputs, and here you have got this clock generator and this AEN, IOB, etc. These pins, they play a very important role in the operation of this 8288 bus controller, right? So let us discuss the meaning of these pins, etc., one by one. So let me just first begin by ALE. So ALE, we already know ALE is used for this address latching mechanism, etc. DEN, this is used to activate the trans receiver. This is what we are also aware of. Then this DT slash R, we are also aware of this particular pin. Then this MCE slash PDEN. This MCE means Master Cascade Enable. MCE means Master Cascade Enable, and this PDE, that is PDEN, it simply means Peripheral Data Enable, right? So this pin has got these two meanings if it is set or reset. Now, what is MCE? MCE is Master Cascade Enable, and this Master Cascade Enable is used to control the mode of operation of another IC, which is called as 8259 interrupt controller, right? So that interrupt controller IC, which is 8259, it can operate in cascade mode. So when we will study that particular IC, interrupt controller IC, this thing will become more clear to you. But then for now, it is sufficient for us to know that this MCE is used to make that IC operate in this cascade mode. So for that purpose, this particular pin is being used when MCE signal is activated, and peripheral data enable, PDEN, is the another meaning of this particular thing. Then we have already studied the meaning of this MRDC, which stands for memory read command, MWTC, which means memory write command, IORC, which means input output read command, and IOWC, input output write command. INT bar we are also clear with. Then let us now move on to these signals. Clock is simply a signal which has been taken from this particular 8284 IC to be able to operate this 8288 bus controller. Then let us now discuss these signals. So this let us first begin with this signal IOB, AEN, and this GEN signal, right? So all of these pins that you see here, they are actually used in maximum mode of operation. These signals that you see here, they are already used in maximum mode of operation. So if you talk about this AEN bar, this is actually used to activate or deactivate certain pins from this AEN bar. These pins are used in multiprocessor system with single processor in the system. This AEN bar and this IOB are grounded. So both of these pins are grounded if you are using it in a single processor system. So although this configuration has been set up for multiprocessor system, but as of now these two pins have been grounded. So that means we are using only one 8086 microprocessor system, but that does not mean that this makes it a minimum mode of operation. So if you do not have multiple processors in your system, or if you have been using multiple processors in your system, but you have removed them at certain point of time, at that point you have to ground these two pins, right? So this AEN and IOB are grounded when CEN is, and then this CEN is also tied high. So this it will be supplied a high logic level value. So when this configuration is there, it simply means that we are only using one processor in our system. And if we want to use multiple processors in our system, then you have to set their values accordingly. What will AEN bar do? So this AEN bar, it actually causes the 8288 to enable the memory control signals. So we have seen this 8288 bus controller. So this memory control signals, I mean these signals will be enabled. So this act as a enable for that. And when other processors are connected into this particular circuit and this AEN bar is enabled, that means when this particular signal will be enabled, so these memory signals will be activated to deal with those processors, right? So similarly, this IOB signal that you see here, this IOB signal, this is actually used for input output bus mode, right? Input output bus mode. And this signal, it actually selects the input output bus mode or the system bus mode operation. I mean, when several other microprocessors are working with this 8086 microprocessor, then to select the appropriate bus mode, this IOB signal has to be activated. So this IOB is used for that purposes. And the CEN signal that you see here, the CEN signal is called as control enable. So it interrupts the CEN signal. input enables the command output pins on the 8288 IC. So the command output pins, they will be activated on this 8288 IC. So this is the 8288 IC, and you have various command outputs here. So whatever are the command outputs, they will be activated by this CEN pin. So this is command enable. So that is the purpose of these three ICs. And when you assemble your computer, it exactly becomes clear to us what configuration we will be using in maximum mode, how many processors will be there. So accordingly, we can set or reset this pins. But as of now, if you say this CEN bar is high and this AEN bar and IOB are grounded, so that means that we are only willing to have one processor in our system, right? So this is a little bit more description of this 8288 bus controller. And let us now see this complete system. Let us now see this complete system of maximum mode of operation of this 8086 microprocessor. So now you can see here that this 8264 clock generator is here, which is connected to 8086. You have also inserted some weight generator here, and then you have 8288 bus controller IC, 8282 latch or 8286 trans receiver, right? So all of these are connected in this fashion, and to be able to activate these latches and trans receivers, you have got this DEN, DT/R and ALE signals. So they are connected to these things. And in the same way we use this externally interfaced memory. We have two EPROMs here, which are odd and even. Similarly, RAMs, which are odd and even, are also placed here, and input output devices are also here. And there is this some address decoding logic. Then again, these control signals, as you see here, memory read, memory write, advanced memory write, input output write, input output read, etc., are all there. They are connected to this system, as well as these will be taken to the other microprocessors in the system to control them. Right. So there is not much difference between the minimum mode of operation and the maximum mode of operation. They both are similar with some differences in hardware. And this difference will be manifested into the study of timing diagrams. When we will study the timing diagrams, there will be some difference because of this change in hardware, because of the introduction of this 8288 bus controller, right? So let me just show you the read operation of maximum mode in 8086. So this is the read operation. To be able to interpret this correctly, let us see some key points about the maximum mode of operation. So this is what happens in maximum mode of operation. And as I told you earlier, that in maximum mode of operation also, in these four T states, the similar operations will happen. The only change will be the hardware signals that you see here. Because of the additional introduced hardware, you had some additional signals, and they have to be set and reset. So let us begin with this T1 state. Before T1 state, this S0, S1 and S2, which are the status output signals from the 8086 microprocessor in the maximum mode, they are set at the start of the bus cycle, right? So when the operation for a particular bus cycle begins, these signals are set, and accordingly, whatever is the value, the appropriate operation has to happen. So suppose we are doing a memory read or memory write operation. So for that, S0, S1 and S2 will have appropriate values, and it will be set before the T1. So in T1 state, what will happen? Simply ALE has to be enabled. Now this ALE is not the ALE of the microprocessor. This ALE is the ALE of the external controller that we have introduced additionally now. So let me again show you the diagram for that, so that the things become clear. So you can see that this ALE, it actually comes as an output from this 8288 bus controller. So from the bus controller, this output has come. Earlier in the minimum mode, some pins out of the microprocessor's output were interpreted as ALE, but now this time this ALE is there. So this ALE has to be the ALE of the bus controller, right? And then DT/R signal, DT/R bar signal is also the signal which comes from the bus controller. So that signal has also to be activated, and then the 8282 will latch the addresses. So these addresses will be latched by the externally interfaced 8288 latch IC. So three will be there in the group. Then in T2, definitely DEN bar signal has to be made 0, because we want to activate the trans receiver as in the case of minimum mode. But again, the point of difference is this DEN bar also does not belong to the microprocessor 8086 now. So if we can see it here, that this DEN bar signal, DT slash R signal, and ALE signal, they now belong to this bus controller IC, right? So that is the point of difference. Otherwise, if you see from this theoretical aspect, the signals that were activated or deactivated were essentially the same. Now, when this DEN bar signal is made 0, this will also enable MRDC and IORC, right? So this MRDC means this is memory read command, and IORC means input output read command. So whether you are doing the memory read or the input output read, the appropriate controls will be initiated. And once they are initiated in this T2 state, they will remain active till T4 state, right? So this is also one important point to note. And in case you want to have an advanced memory write control or advanced input output write command signals, then they will be activated. They will be also activated until T4. So whether you want to have a normal memory read operation or advanced memory write operation, so they are activated till T4. The only point of difference is normal memory read operation. In the normal memory read operation, if you see, it will not remain active in this particular range. So that we will discuss when we will discuss T3. So inside T3, the data transfer will happen. This is the primary task of T3. Then insertion of additional wait states, that is TW states, if it is required. This is also clear to us from the previous lecture. And if you are performing this operation of MTWC bar and IOWC bar, that is you are trying to read this input output write command or this memory write command in a normal mode, then they will be activated until T4. They will also be activated until T4. Then the status bits, they will remain active until T3. The status bits will remain active until T3. The status bits that were set at the beginning of a particular bus cycle, they will remain active until this T3 state. And if you see this T4, if you see this T4, it will correspond to the deactivating of various signals, right? Another important point to note here is that you see this normal memory write operation or normal input output write operation and the advanced memory write and advanced input output write operation. So you see that this advanced operations, they get activated from T2. However, the normal operation, they get activated from T3. So this advanced operation is ready one T cycle beforehand this T3, right? So your if the slow peripheral is interfaced with this 8086 microprocessor, in that case, it will get a time of one more time slots or one more T state to prepare itself for this data transfer operation, right? So now let us come to the timing diagram of the read mode operation in 8086. So if you have seen the hardware and if you have understood what should happen in what cycle, so let us begin from this T1. So let us see the status of this S2, S0 to S2. That means S0, S1 and S2 bar. If you see the status, it has been set beforehand. I mean, before the beginning of T1, the status has been set. And this will be set till T3, right? And after that, the address status and BHE and H7. So we will discuss this signal after we discuss this address latch enable. So in the beginning T1 cycle, if you see the T1 cycle, this address latch enable signal has to be activated. So this is activated somewhere in between this T1 cycle and it will be activated. And you can see that the address data which will be contained on AD0 to AD15 plus this bus also. It is kept here in this particular T1 cycle. So I think this clock cycle has been shifted a little bit back. It should have been a little bit forward. So these two addresses will be latched. Then after in the T1 cycle, these two addresses have been latched. Let us see this DEN signal. This DEN signal, DT slash R signal, they have been activated in the T2 timing cycle, right? So they have been activated here and they will remain activated till T4, right? And accordingly, when they are activated, you can see the this address bus actually becomes the data buses. This address bus actually see that the upper portion of this will show some status bits because the interpretation of the last four bits of addresses is status, so it will be provided there. And if you see the address from AD0 to AD15, which is the data bus, so it will remain deactivated there. In the T3 cycle, so this should have been a little bit forward here. And this, in the T3 cycle, the actual data transfer operation takes place out of this data bus. So this data transfer cycle will happen, and the last phase, which is the T4 cycle, all of the signals will be reset. So this is in sync with what we have just discussed according to this particular thing. So the only point of difference that we saw in today's lecture was in the hardware, and it was not in the software. And accordingly, the new signals that were introduced because of hardware were also to be set or reset. Right. So for this, I think this is a sufficient explanation for this maximum mode. So this has been a short lecture, but there was nothing new to tell in this. So it is just a different way of organizing our computer system. If multiple processors are there in our system, then this mode can be used. So this is it for this particular video lecture. I will see you in the next video.